Welcome back to the classroom. My name is Mr. Wong. Today we'll be explaining the Module 5 Inquiry Question 1 exam question. This is going to be taken from the 2017 HSC Physics paper, question 29, worth 7 marks. We have a spring that's used to construct a device to launch a projectile, as you can see from this construction here. The force required to compress the spring is measured as a function of displacement by which the spring is compressed. So that's what we're measuring here, the force applied and the displacement of the spring. Moving down. The potential energy stored in the compressed spring can be calculated from the formula of U equals half kx squared, where k is the gradient of the force displacement shown in the graph here. Okay, so if I draw a line of best fit, and I'll do this freehand, so you should be able to do one a little bit more straight than the one I'm gonna do. Not too bad for freehand drawing of a straight line. A projectile of mass 0.04 kg is launched using this device with a spring compressed by 0.08 meters. Calculate the launch velocity. Okay, so coming back up here, let's just work out if we have a displacement compression at 0.08 and we want to find the launch velocity, so we're trying to find U. So what we'll need to do first is find the value of k, so our gradient, so our rise over our run. So drawing the graph out, so it looks like our line comes along like here. So one of our points here will be 0.08 to 25, or 24, sorry. And this point that we have here is 0 and 1. So if we measure off our gradient here, this is what we'll end up getting. So put it into your calculator. So I get a number that is 287.5 joules. Okay, I'm going to just bring myself back down to the working out here. So I know that K is equal to 287.5 joules. You can just make it say working on graph. I know that the potential energy is half kx squared. At the same time, in saying that, we know that when we're storing that energy, so when potential energy is being stored up, there is a decrease in kinetic energy. But when potential energy is being released, so when the spring is being compressed out, the kinetic energy will rise back up. So we can say that the potential energy from the compression will be equal to the kinetic energy of the spring coming back out, and that'll be half mv squared. So that v squared will be the velocity in which the object will be launched out. Okay. Next we already know what k is, that's 287.5. times the displacement that we have here, 0.08 squared, equals to half. Mass is 0.04 times the velocity, which is what we're trying to find here. So let's rearrange all the things to the other side and then try and find an answer. So we have our half here, so times both sides by 2, so that will cancel out the half here. So we're left with 287.5 times 0.08 squared. Okay, we need to get rid of the 0.04 from the v squared, so divide both sides by 0.04. Okay, so we get v squared. Obviously now we need to square both sides, so v equals the square root of the value we just wrote up there. Obviously, if you think it's tedious to do this step up here and just go straight to this step, that's fine too. Okay, so the velocity we have, we get a velocity of 6.7823299983 meters per second. Let's have a look at how many sig figs they use. One here, so 3 sig figs here. Let's just do a round off to 2 decimal places, because they do that, so we'll round it off to 2 decimal places. So 0.78 meters per second, 2 deci places. And that's how you solve the first problem, which is working out the launch velocity there. We know this because there is a change between the potential energy to kinetic energy. Alright, next question. It says, calculate the range of a projectile launched by this device from ground level at an angle of 60 to the horizontal with a velocity of 10 meters per second. So we're launching it at 60 degrees to the horizontal, so that's our angle there. We're trying to work out the overall displacement from that. So based on the equation we need, if you recall, uxt. Now we don't actually know what the velocity of ux is here. Although it says we have a launch velocity of 10 meters per second, that's not the same as saying ux is 10 meters per second, because it's this diagonal component here. If you remember from vector analysis, if you have a diagonal component, it also has a vertical and horizontal component. So we need to find the horizontal component for this. Okay, so if you draw out your triangle again, and that's 10 meters per second. To find this component here, you have the angle, and assuming we are launching it like a right angle triangle, that's our hypotenuse, that's our adjacent side. So we are going to be using cos theta, which is the using adjacent and hypotenuse side of the right angle triangle. Okay, so it's cos 60 times 10, and that will equal, just grab that back, and that will equal to our ux. So putting in my calculator, that is 5 meters per second in the horizontal launch direction there. Okay. Next part is to work out the time in which it's taken for our object to launch. So if you actually look at the question, it doesn't actually ever mention launch time or the time it takes for the projectile to move. And obviously when you do this question at the start, you'll might find it a bit confusing how you could work out the overall launch time. I want you to think about it this way. When we launch this object at 60 degrees, there will be a point where it stops moving. And that's where we reach maximum height. After that, it's going to then drop back down, and it will also have a 0 velocity. That's obviously assuming we start the launch at a ground level position. Okay, so what we can actually do is we can actually try and work out the time it takes to reach this maximum velocity here, and then we can times this by 2 in order to find the total trip time of this projectile. Okay, so firstly we need to know what the initial velocity is. Okay, and we're going to be using this equation here. So we have Vy equals to Uy plus Ayt. Ay is the acceleration due to gravity. As our object is being launched up, that means if gravity is going in the opposite direction, you need to consider that in your vector analysis. So Uy is 10 times sine 60. As you can see from our triangle here, we have the hypotenuse of the 10, and then we have the y component that we're trying to find. Ay will be minus 9.8 because it's going in the opposite direction in which the object is being launched. And then from there, we should be able to work out the trip time. Once we're done, we need to plug it back into this equation. Okay? We also know that Vy is going to be equal to 0 because it reaches maximum height. Okay? So that's what we're dealing with here. Just change that to a positive. Okay, so it'll be negative 10 sine 60 divided by negative 9.8 equals to time. And so the total trip time we get, once I plug it into the calculator, is 0.883699 seconds. So I'm going to plug that into this equation up here. Okay, so once you found that, remember this is just half the amount of time, so maybe even if in your calculations you just want to acknowledge that it's half the amount of time that's passed. Okay, so the total trip time, or T total, is going to be 1.76 seconds. So plugging that into my calculation now, Ux was 5 and we already have T total here. So that gives us a value of 8.8993,916 meters. Rounding it off to 2 decimal places, being consistent with my answer above, be 8.84 meters, 2 deci places. And that's how you do the question. This is quite a lovely question because it actually takes into account law of conservation of energy and also looks into projectile motion as well. So it really covers quite a few points from Module 5. Hopefully you found the video useful. Give it a like to support future videos coming out, and thank you for watching all the way up till now. Take care.